Okay, we've been learning that randomization helps balance out lurking variables. The idea is that if you randomly select your subjects into two groups, you're going to balance out any lurking variables so that they'll be split 50-50, and then if there's a difference in the groups, you can attribute to whatever treatment that you're applying or investigating. Um, but what? So good experiments require careful attention to details, making sure that you've accounted for all those randomization problems, all those lurking variables as much as possible. Some things that you need to be aware of are things like if you give one group a placebo is some sort of dummy treatment, usually in the form of like a sugar pill or something, where the subject thinks they're receiving the treatment, in reality they're not. And when they have a response to that dummy treatment, it's called the placebo effect. The idea is that they think they're taking a pain medicine, and so they make sure that they have less pain, even though they only took a sugar pill and had no effect on that. Whenever possible, you should always do experiments with humans that are called double blind. Double blind experiments are where you randomly select which group is going to get the treatment, and when you're passing out the treatment, the person who's passing out the treatment doesn't know who's getting the treatment either, because you don't want them to introduce a bias and by picking on certain people getting the treatment and other people not. So the best kind of experiment is what's called a double-blind experiment, where neither the person who receives the treatment nor the person who gives it know who's getting the treatment and who's getting the placebo. Here's a problem that we're going to be looking at in class over the next day or so, and I'd like you to start thinking about this. Here's a plot of land that is a square, and a farmer owns this, and he has divided up into 16 smaller plots. And each of these plots he's going to plant some corn, and he wants to know what would be the average amount of yield that he would get for all of his land. And we're going to randomly select 4 of these plots, find out what the yield was, add them up, and find the average. Well, notice here that there's a river over here on this side of the land. And so we're going to take a look at a simple random sample. We're also going to look at a sample where we divide it into rows and take one from each row. And we're going to look at a sample where we divide it into columns and take one from each column. And I want you to think about that. A simple random sample would randomly select any 4 of those plots. If we divide them up into rows, then we would randomly select one from each of the rows. So we would randomly select one of the plots from 1 to 4, then one of the plots from 5 to 8, 9 to 12, and 13 to 16. A third way that we're going to look at is what if we were to split them up to columns first and then randomly select one from each column. Okay, and the idea is that which of those 3 methods do you think might get the closer to what the actual average turns out to be? So just think about that, and I'm going to ask you to make a guess of that, and then we're going to experiment and see what happens with that. Okay, when we do experiments, we like to infer from our sample, based on what we see in our sample, we like to infer what's going to happen to the whole population. So if we get results in our sample that are far away from what we would consider normal, then we can say that our treatment is having some sort of effect, and therefore infer that that treatment would have the same effect on the population. The idea is that the larger away our results are from what we would consider normal, we would call it statistically significant. Statistically significant is usually a good thing if you're running a science experiment. You want to see results that are far away from the normal, because that means that your treatment is having some sort of effect or making some sort of difference from what would normally be happening. A statistically significant association of data from a well-designed experiment does imply causation. If you have a well-designed experiment and you can show that there's a big difference between your treatment and not giving your treatment, that means that your treatment is having some sort of effect, hopefully a positive effect. Okay, let's take a look at a type of random sampling that we need to use sometimes. when there's a situation where we know that there's a difference in, let's say, an area. Um, the the best method of sampling will always be a simple random sample, because then every area or every subject has an equally likely chance of happening. But there are times when that will not give us the most precise results. There are times when we may need to look at the fact that, hey, we're looking at the effect of the growth of algae in these petri dishes, and we're putting them inside a room where there's a heater on one side of the room and there's an open window on the other. So we recognize that that is a variable that we wanted to check. So we're going to take all the beakers that are close to the window, put them in a group, all the beakers that are close to the heater, put them in a group, and randomly select from each of those groups. This is an example of a blocking. We will recognize that there's some sort of external factor there, and we want to randomly select from groups that are represent each of those factors. So a randomized block design is a random assignment of experimental units to treatment carried out separately within each block when we know that there's a known variable here. The bottom line is that you've got to control what you can, block on what you can't control, and then randomize to create as comparable groups as possible. Another very common experimental design is what's called a matched pairs design. What we do then, the most common example of this is when you have a subject take a measurement of some kind, let's say take a heart rate, then you have them do something, run up and down the stairs, and then you have the same subject see what their heart rate is after running up and down the stairs. This is a matched pairs design because we're taking two measurements from the same subject, so it's being paired off. We know a before and after. Another example would be to randomly select 50 people in two groups, and we're trying to measure the effect of, let's say, their stress level. So we pick the 50 people and we ask them to evaluate their on a scale of 1 to 10 how much stress they have on a daily basis. And the two people that have the highest amount of stress, we pair them off. The next two people who have the next highest, we pair them off. All the way down to the two people who say they have the lowest stress, we pair them off. We do some sort of an experiment and we see if there's an effect on their stress level. That's another example of a matched pairs design. We still use chance or random sampling to determine which unit in which pair gets each treatment. So if I were to use my example of the stress level, I would then flip a coin or roll a dice or do some sort of random number table and decide those two people who had the most stress, which one gets the treatment and which one gets the placebo. So that there's still randomization and there's chance. We're not biased in any way. Okay? So that's what we call a matched pairs design, something you need to become very familiar with. Again, two different types. One where it's within the same person, you're taking a measurement before and after, and another where you kind of rank your two groups from highest to lowest, and you match up the two highs, the next two highs, all the way down to the two lows, and you compare their results. As we get into very complex statistical problems, we're going to give you a way to organize that problem. And if you follow this process on every one of these problems and you do them correctly, you will do very well on the AP exam. It is a 4-step process that we're going to ask you to do every time we solve any kind of statistical process. The first step is to state, what is the question trying to answer? Put it in your own words, put it in context, tell me what is being asked of you. Plan, how will you go about answering the questions? What statistical techniques does this problem call for? What criteria have to be met to be able to put your action into plan, to actually do it, okay? The last step is to the third step, and that's usually to making graphs, carrying out any calculations, actually doing the math. The do is the math part of it. The conclude then is then to, like I've been talking about, is then to make sense of that number that you're going, or numbers that you're going to get, and explain in context what that means for the people or that are interested in your problem to be that's being solved. So it's always state, plan, do, and conclude. Last year's AP Stats class came up with a little mnemonic device that helps them remember this. Give credit to Christian Bayoka and Austin Corpuz, who said that state plan to conclude. The easy way to remember that is that Spanish people do the dance the cha-cha. If that helps you, great. If not, it's okay too. It's just an example.